Hey guys, I'm going to have a quick tutorial video on how to run FEA for some of you that maybe haven't done it, and show you what you're going to want to look for when you do a test on a part. So we'll start with, I've got two parts that we'll look at. We'll start with Robert's bell crank that we have here. So if you don't already have it open on the computer, go to Tools and Add-ins, and you're going to want to hit this checkbox for SolidWorks Simulation, and that'll open it all up. Then you'll go to the tab. You can hit New Study Advisor, and SolidWorks will walk you through it, but it's a real pain and I don't recommend it. So we're going to hit New Study. SolidWorks has a lot of different types of studies that you can do. I have not done most of these, and in all likelihood you guys will never do anything but a static analysis. Maybe a fatigue analysis if we did a lot of aluminum parts, but our parts never see enough cycles to really worry about that. So we're going to do a static one. Because you guys are working in the Dropbox with these parts a lot, it's a good idea to move where the simulation files go because they do take up a lot of space. So to do that, you right click on the static, hit Properties, and then your Results folder. You can change it in here. I just do mine on my desktop in a Scratch folder. Okay, so the three main things that you need to run a simulation is you need correct fixturing, a load of some sort, and a mesh on the part. Depending on what you're doing, sometimes one of these can be a real problem. With a lot of these parts, they're simple enough that it's not really a big deal. So a quick lesson on how a bell crank works is it rotates about this axis when the push rod gets pushed by the wheel and then compresses the shock. So it's connected by two force members. So the loads going into the bell crank are going to be perpendicular to the holes basically. So what we're going to do is we're going to start with our fixturing. Because these parts can rotate, we will kind of model that. So we're going to start with a fixed hinge. SolidWorks 2014 has these nice images to show you what each mate pretty much does. So as you can see, a fixed hinge is exactly what it sounds like, a hinge. So we'll put that on there where the bearing goes, hit check, and then our part isn't fully defined because it could still move laterally. So we have to go in, and SolidWorks will pop up an error if your part's not fully defined, and then you'll have to go back and figure out why and where you need to put stuff. So we'll put fixed sliders or roller sliders on each side here, and our part should be fully constrained. Now, since we have our fixtures, we're going to come in. There's a bunch of different forces you can use. The only two you're probably going to care about are torque and force. So this one's going to be a force, not on that face. So our forces are going to be from the reaction force from the shock and the push force from the pull rod. So we're going to click the inside of that hole and that hole, and we're actually going to change the direction because it's not a radial force. And while it should technically go in this line here, we're just going to select this one for ease of the video. And then we're going to put, we'll say 30 foot-pound or 30-pound force on it. Got to be careful if you do hit enter after you enter something like that. Sometimes it will change your value back to the base value. So right now, this is putting 30 pounds on this hole and 30 pounds on this hole, or 15 pounds on this hole and 15 pounds on this hole. So if you wanted 30 on each, you hit per item. We want it just total. Then we're going to do the same thing on the opposite side. We want our selected direction. You can also select a face if you wanted, and then use these for your different directions. Doesn't necessarily have to be a line. Boop doop. 30 foot-pounds. Keep saying foot-pounds, just pounds. Check. All right. So we've got our constraints and we've got our forces, so we have our mesh left. So you can just hit mesh and run, and SolidWorks will automatically create a mesh. It'll just be the standard default mesh. Depending on what you're doing, that may be fine. We're going to create our mesh. So if you hit mesh parameters, it'll show you two different types of meshes. I'm going to show you another part where you can see the difference between a standard mesh and a curvature mesh. This part doesn't show it very well. But for this part, we're just going to do a standard curvature mesh. We'll make it nice and fine. So the fine and coarse setting on the mesh defines the size of these triangles. So obviously the more coarse it is, the less area each triangle represents. So you have a more blocky result view. So we've got our three things. We've got our forces, our part's fully constrained, and we've got our mesh. So we can hit run up here. And Cosmos will do a thing. Oh, maybe our part's not fully defined. So sometimes if your part's not fully defined, you'll get a pop-up like this asking if you want to do small or large displacement. We don't want large displacement. And we can look at this displacement, and it moved 6 times 10 to the 8th millimeters. So something obviously wasn't constrained because it's just pushing the part off the screen, more or less. So we'll go back in and we'll just add a fixed geometry and then delete the other two. And if you have a fixed geometry on a part, it is pretty much always constrained from movement. So we'll rerun again. We had no large displacement. You can see the part looks kind of funky now. It looks like it's going to fail, but while it looks that way, the part moved 0.005 millimeters at the most in this area here. So that is just the deformed result from Solidworks. So it creates a deformed result that's multiplied by so ever 1,000 times, so you can actually see where the deflections are. But you can hit undo on the deformed result and show the regular part, or leave it on. It's up to you guys. But just be wary, while it may look funky when you're done, it may not actually be flexing anywhere near that much. So you've got your stress plot, which we can go in and edit the definition. I don't particularly like metric units for these things myself, so we can go in and change it to PSI. And your scale now is in PSI, and you'll have a yield strength down here. And the scale automatically scales to min and max pressures on the part. So our max PSI on here is 1800, where our yield is 40,000. So we're not even close to yielding this part yet. When we talk about parts, one of the big things we look at is safety factor. And safety factor, if you haven't learned yet, is basically just the relation of this von Mises stress to the yield strength. So SolidWorks so happily lets us make safety factor plots so you can see those things. So you right click on results, define safety factor plot, and then most of our safety factors are von Mises stress based, so you'll just hit that and hit check, and it looks like a lot of red, but again, that's SolidWorks just doing default things. So what we're going to do is go to chart options. We're going to show minimum safety factor, maximum safety factor. We're going to change this whole scale to a max of 10 and a min of 0. So that'll change the colors of the part. And then we're going to go to floating points. You can actually see what the values are. Oh, I don't think it changed. Try this again. I don't know why it didn't take it. There we go. So you can see our minimum safety factor is 21, so it's well above 0 to 10. So basically, if you don't know what safety factor is, anything at 1 or below is going to fail at that point, and anything 1 or above is below the yield point of the material you're using and will be safe. So when you're designing for formula, we often shoot for a safety factor of 1.5 just to make sure it's light enough but still safe, because you don't want it to break your first time out. Subsystem leaders will be able to give you better tips and advice on what we're looking for parts. So we're going to look at this other part, so I can show you the difference between a standard and a curvature mesh. So we're going to do the same thing, new study, static. We're going to apply our fixtures. This one we're just going to apply a fixed geometry on the inside here and see how much torque it takes to break it. Go to external loads. We're going to do a torque this time. We'll just apply it on this face. When you do a torque, it'll ask you for a cylindrical face or an axis of the part. So we'll give it that. We have foot-pounds. We'll put 1,000 foot-pounds on this piece because it's pretty strong. A more representative simulation of this piece would be to put the torque on each of these splines, but I'm not too inclined to click on all those splines right now. So we've got our fixtures down here. We've got our torque up here, so we need a mesh. We're going to hit create mesh. Now I'm going to show you the difference between curvature-based mesh and standard mesh. So we'll hit curvature, make it fine. If you're doing large things, make your mesh less fine, but for a single part like this, I usually make it pretty fine because the computer handles it fine. So as you can see on this part where we've got some fillets here, the mesh area gets smaller around the fillets and it's larger along this spindle area because the computer figures out that this is a stress concentration area, so that gives you a better resolution on it. So then we'll make a standard mesh, also make it fine. So the standard mesh, you'll see all of the mesh triangles are the same size no matter where they're at. So they all cover the same area basically. So if you do a standard mesh, you can go in and create a mesh control. So let's say we're really worried about this fillet breaking for whatever reason. So we can hit that and we'll make it super fine and apply it, and then we will rebuild our mesh. And hopefully, if I did it right, it should be smaller around this fillet. Yeah, so you can see how our triangles are smaller around the fillets to give better resolution in high concentration areas. My recommendation is just use a curvature mesh. Let the computer work for you. There's no reason to do a standard mesh with mesh refinement unless you run across a part for whatever reason that you can't actually use a curvature mesh. Have our mesh. Oh, so this part doesn't have a material defined. So you'll right click on this, apply edit material, and we'll just pick something. And so it looks like our part is completely deformed, but we will look at the displacement plot and you can see it moves 0.03 millimeters. So while it looks like it's deformed a bunch, it actually hasn't. So again, be wary about the deformed results in Solidworks. It can kind of skew your perception of what's happening. And that's about it. So if you guys ever have any questions on running an FEA, talk to your subsystem advisors. Most of them are pretty good at running this stuff, so they'll be able to help you on whatever you need. All right.